Hey guys, tonight we are leaving the solid, predictable ground beneath our feet and soaring out to the darkest, quietest corners of the cosmos, where stars and therefore you are born. Imagine you are no longer constrained by a body. You are pure awareness, a consciousness drifting into a space so impossibly vast it makes our solar system look like a tiny, forgotten marble. You find yourself suspended in a realm of utter blackness. Yet it's a blackness pregnant with potential, the literal stuff of creation. This is a giant molecular cloud, ZEE, a massive swirling nebula that might stretch for hundreds of light years. The temperature here is staggering, plunging down to maybe only 10 to 20 Kelvin, that's 263. Azerble, Celsius, or 440. Azerble, Fahrenheit. A chill that would instantly freeze every breath, every memory, and every drop of water you've ever known. It's so cold, it almost feels warm compared to the sheer nothingness around it. You are surrounded by an almost incomprehensible amount of material, mostly molecular hydrogen and helium gas, but also complex carbon compounds, silicates, and tiny frozen particles we call cosmic dust. If you could somehow scoop up a handful of this interstellar material, you'd be holding the atoms that will someday form planets, oceans, and maybe even a slightly grumpy cat. Here's a cool detail. While these clouds are incredibly massive, they are also incredibly low density. A cubic meter of the gas and dust out here contains about 1 million times fewer particles than a cubic meter of the air you're breathing right now. So, even though there's so much stuff, it's incredibly spread out. It takes billions of years for this sparse material to collect and form anything coherent. Now, focus your non-existent senses on the darkness. You begin to feel something subtle, something almost imperceptible, yet it is the most powerful force in the universe: gravity. In a GMC, tiny initial irregularities, denser pockets of gas, or a slight compression caused by a passing supernova shockwave start the whole process. Think of it like a cosmic traffic jam. A few more hydrogen molecules happen to be in one spot, and their combined gravity attracts a few more, and a few more. It's a runaway process, slow motion, but unstoppable. Historians still debate whether external shockwaves, like supernovas, or internal turbulence, is the primary trigger for the initial collapse in all star-forming regions. But either way, the dust and gas in your immediate vicinity are starting to move inward. You are essentially floating in a very large, incredibly slow-moving celestial avalanche. This is the stellar nursery, and you are at the beginning of a star's life. You might joke that the GMC is just a giant cold cloud trying to be famous, and its only tool is a tiny amount of self-doubt that makes it contract. A solid historical fact is that the first giant molecular clouds were only clearly mapped and understood in the mid to late 20th century with the advent of radio astronomy, as the molecular components of these clouds emit radiation primarily in the radio and microwave spectrums, invisible to the human eye. This means for centuries, the birthplace of stars was literally invisible to us. Look around. That faint starlight you see in the distance, piercing the gloom, is an ancient star, perhaps one that will soon share its energy with a new neighbor. The gravitational pressure on the material around you is getting stronger, but it's still far too gentle to hurt. You probably wouldn't survive this era in a physical body, as there's no light, no warmth, and certainly no breathable air. But as pure consciousness, you are perfectly safe, watching the slow grind of celestial mechanics. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know where you're listening from and what time it is for you in the comments below. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's drift into tonight's story together. That almost imperceptible slow-motion pull you felt in the giant molecular cloud GMC is accelerating, though still at a cosmological pace. You are now inside one of the denser, gravitationally dominant regions within the cloud, a localized pocket that has begun what astronomers call fragmentation. Think of the GMC like a massive, churning body of water. Now, smaller whirlpools are forming within it. These fragments, perhaps a few light years across, are where individual or small clusters of stars will be born. The material around you, primarily hydrogen and dust, is no longer just drifting, it's streaming toward a common center of gravity, which happens to be exactly where you are floating. As the gas rushes inward, an incredible process begins. Conservation of angular momentum. Imagine an ice skater starting a spin with arms outstretched. As they pull their arms in, they spin faster. The cloud fragment, which had a slight rotation to begin with, starts spinning faster and faster as it shrinks. This rotation causes the material to flatten out into a rotating disk, known as a protostellar disk or accretion disk, surrounding a central, increasingly dense core. You are essentially floating in a massive, flat, swirling celestial pizza of gas and dust. This spinning disk is not just a beautiful sight, it's the factory floor for future planets. Here's a curious detail. While most of the gas falls onto the forming star, some material is channeled to the poles of the rotation, where it is shot out into space as powerful, opposing jets called bipolar outflows. These jets look like giant cosmic fountains bursting from the nascent star and are a clear sign that a protostar is actively feeding and growing within the disk. It's the universe's way of clearing its throat before the grand performance. As the material in the core piles up, the pressure becomes enormous. Remember how cold it was in the GMC? That extreme cold prevented the gas from generating high internal pressure and resisting the collapse. Now, as the core contracts, the gravitational energy is converted into thermal energy heat. The temperature at the very center begins to skyrocket, climbing from a few degrees Kelvin to hundreds, then thousands, and eventually millions of degrees. The center is glowing intensely in infrared light, though the surrounding dust disk is so thick and opaque that very little visible light escapes. You are now witnessing a protostar. It is a star to be a baby that has yet to take its first true fiery breath. A solid historical fact is that the Hubble Space Telescope and later infrared telescopes like Spitzer were crucial in detecting and studying these deeply embedded protostars and their disks because the visible light is blocked, but the heat radiation infrared can pass through the obscuring dust. The protostar state can last anywhere from 100,000 years for the most massive stars to 100 million years for a star like our own Sunday. The duration depends entirely on how much material the core can gobble up from that surrounding accretion disk. You might notice that things feel a little fiery now. It's warm, maybe even a little scorching, but it hasn't exploded yet. It's like watching a kettle boil. Only the kettle is 10 times the size of our entire solar system, and the boiling takes 1,000,000 years. Historians still debate whether the rate of accretion, how fast the protostar gathers mass, is steady or occurs in bursts, which fundamentally affects how long the star remains in this prenatal state. One light joke: it's a good thing this protostar phase takes so long. Imagine the cosmic baby shower invitations you'd have to send out if it happened in a hurry. The gravitational collapse has been successful. You are no longer in a loose, cold cloud. You are near a dense, hot, turbulent core that is actively drawing in matter and preparing for the moment of truth. You are now deep within the protostar, that immensely hot, dense, and rapidly spinning core, and the pressure from the surrounding accretion disk is still fueling its growth. If the gravitational collapse was the long, slow first act, this phase is the dramatic, turbulent preparation for the star's grand debut. As the core continues to compress, the heat rises inexorably. We're talking millions of degrees Celsius now, but it's not quite hot enough to fuse hydrogen. The star-to-be is still relying solely on the heat generated by the kinetic energy of the collapsing matter, which is why it hasn't truly turned on yet. This period is marked by an incredibly curious and violent intermediate phase, known as the T Tauri phase, named after the prototype star in the Taurus constellation. During this time, the protostar is not yet fusing hydrogen, but is highly active and erratic. Powerful, magnetic field-driven bursts and solar flares, far more intense than anything our sun produces today, erupt from its surface. Remember those bipolar outflows, the jets of material shooting out from the poles? In the T Tauri phase, these jets, along with intense stellar winds, become critical. They act like a giant cosmic broom, sweeping away the remaining gas and dust from the surrounding protostellar disk. You watch as the thick, dark shroud that once obscured your view thins out, allowing the first glimpses of the core's white-hot surface to finally shine through. It's like the stars blowing a gigantic ring of smoke out into space, clearing its immediate neighborhood. This clearing process is essential because it shuts off the star's primary food source. Once the wind clears the majority of the disk, the accretion stops, and the star reaches its final, near-stable mass. Without new energy coming from collapsing material, the internal pressure starts to dip, and the core tries to contract just a little bit more. This slight final contraction is the tipping point. The temperature and pressure at the core finally hit the magic number, around 15 million Kelvin. At 15 million Kelvin, the strong nuclear force triumphs over the electromagnetic repulsion between hydrogen nuclei. The core becomes hot and dense enough for thermonuclear fusion to begin the transformation of hydrogen into helium. This process, specifically the proton-proton chain, is the ignition switch for the star. It's the moment the star is truly born. The immense energy released by the fusion process provides a powerful outward pressure that perfectly balances the inward crush of gravity. This is known as hydrostatic equilibrium. This balance stops the gravitational collapse that started eons ago and locks the star into a stable, luminous existence. A solid historical fact is that the T Tauri stars were first recognized as a distinct class of variable stars in the mid-20th century, characterized by irregular light changes, strong stellar winds, and emission spectra indicating significant surrounding gas and dust. Historians still debate whether the intensity and duration of the T Tauri phase significantly influence the ultimate formation and survival of close-in planets, like the hot Jupiters in the stars system. It's the universe saying, "I'm here, I'm bright, and my powerful stellar winds are going to give everyone a bad hair day." A curious detail: the immense energy released by hydrogen fusion at the core eventually takes hundreds of thousands of years to travel outward through the star's layers to reach the surface as light. So, the light you see from a star today was generated in the core long, long ago. The darkness is gone. You are now bathed in the brilliant, steady light of a newly ignited celestial furnace. Congratulations, you've witnessed a star's birth. The sudden, steady brilliance of the newly ignited star is overwhelming, a profound shift from the dark, chaotic collapse you just experienced. You are now orbiting a main sequence star, where it will spend about 90% of its active life. This is the era of stability, defined by that perfect truce between the inward crush of gravity and the outward push of thermal pressure generated by hydrogen fusion in the core, the glorious state of hydrostatic equilibrium. If you remember that final little self-compression before ignition, that was the star figuring out its life plan. What happens next? How long this star lives, how bright it shines, and even what color it is almost entirely determined by one single factor: its initial mass. It's a stellar reality show where mass determines destiny. You might be orbiting a star like our Sun, a modest yellow dwarf, which has just the right amount of mass to burn its hydrogen fuel steadily for about 10 billion years. Or you might be near a tiny, faint red dwarf, stars with as little as 8% of the Sun's mass. These little cosmic light bulbs are incredibly thrifty. They burn their fuel so slowly and efficiently that they can live for trillions of years, far longer than the current age of the universe. They are the marathon runners of the cosmos. On the other hand, look toward the incredibly bright, intensely blue stars nearby. These are the celestial sprinters, stars that formed with 10 or more times the mass of the Sunday. They are massive, they are hot, and they are beautiful, but they are also incredibly wasteful. Their core temperatures and pressures are so extreme that they burn through their vast hydrogen reserves at a furious pace. A star 20 times the mass of the Sun might live for a mere 10 million years. It's like they know they're the coolest star in the club and decide to live fast and die young. One light joke: For massive stars, their life plan is essentially be bright, look great in blue, and ignore the financial advisor who suggested saving fuel. This fundamental relationship between mass, luminosity, and lifetime is a solid historical fact, first systematized in the early 20th century with the development of the Hertzsprung-Russell diagram, which plots a star's brightness against its color temperature and shows that nearly all stable stars fall along a narrow curve called the main sequence. Historians still debate whether the initial mass function, the distribution of masses for newly formed stars, is truly universal across all galaxies, or varies depending on the metal content and environment of the giant molecular cloud they 2022 formed in. A curious detail is the relationship between color and temperature. The blue-white stars are the hottest, with surface temperatures potentially exceeding 30000 Kelvin, while the redder stars are the coolest, dipping below 4000 Kelvin. Our sun, the yellow star, is perfectly middle of the road. As you drift here, imagine the massive hot blue star's light pressing against you. That intense radiation is constantly driving material off its surface, contributing to a powerful stellar wind far stronger than the gentle stream of particles from the less massive stars. The star you are currently observing is stable, but its fate is sealed by the sheer volume of fuel it has and the reckless speed at which it's consuming it. It has entered a long, steady chapter, but its eventual dramatic end is already written in its massive, luminous glow. As you continue to drift alongside this main sequence star, remember that balance, the perfect, fiery truce between gravity and the heat of hydrogen fusion. But even in this era of stability, the clock is ticking, and the main sequence lifetime is merely a long, steady countdown until the inevitable core change. Let's shift our focus to a star like our own Sun, a middle-aged yellow dwarf that has been burning hydrogen into helium for billions of years. Right now, the helium, the ash of the fusion process, is building up in the very center of the core. When a star like the Sun has consumed about 90% of the hydrogen fuel in its core, a dramatic crisis begins. The fusion reactions slow down and eventually stop entirely in the center because there's no more hydrogen fuel. Without the energy-generating outward pressure from fusion, the perfect hydrostatic equilibrium is broken. Gravity, which has been patiently waiting its turn, takes control, and the helium-rich core begins to collapse under its own immense weight. This core collapse is what triggers the star's enormous transformation. As the helium core shrinks, the shell of hydrogen surrounding it gets squeezed and heated up intensely. This thin shell is now in a region of much higher temperature and pressure than before, which dramatically increases the rate of fusion in the shell. This hydrogen shell burning generates far more energy than the star produced during its stable main sequence life. This massive surge of energy pushes the outer layers of the star, the parts you are floating near, outward with incredible force. The star begins to swell, not just a little, but catastrophically. The stellar surface expands thousands of times its original radius, becoming so vast that for our Sun, the surface will eventually engulf Mercury, Venus, and possibly Earth. As the star's energy is spread out over this colossal new surface area, its temperature actually drops dramatically, causing its color to shift from yellow to deep orange-red. It has become a red giant. It's like a tired, old engine suddenly deciding to grow 1,000 times bigger and wear a cozy, red sweater. One light joke, it's the stellar version of a midlife crisis, where the star suddenly decides it needs a much bigger wardrobe. This immense expansion marks the start of the star's descent toward death. A solid historical fact is that the concept of stellar evolution, particularly the red giant phase, was largely confirmed through observations of star clusters where all stars formed at the same time but showed different stages of life on the HR diagram, proving that stellar life is a progression. Historians still debate whether mass loss during the red giant phase, the rate at which the star's expanded outer layers gently drift away, is smooth and continuous, or occurs in distinct explosive thermal pulses. A curious detail about the size: if you were to stand on the surface of a star during the main sequence, and then on the surface of its red giant phase, you would be experiencing almost the same amount of gravity, because while the radius has expanded hugely, the mass remains the same, meaning the outer layers are incredibly diffuse, like a thin, hot fog. The fate of the star now diverges based on mass. If it's sun-like, after a brief period of helium fusion, the helium flash in the core, the outer layers will drift away to form a planetary nebula, leaving behind a tiny, cooling ember called a white dwarf. If the star is much more massive, at least 8 times the Sun's mass, it faces a much more dramatic, spectacular death. A final collapse and a glorious supernova explosion, which is the only way to create and disperse the heavy elements necessary for life. You have just witnessed the quiet, expansive death of a sun-like star. But now, we are going to pivot our focus away from the typical stars and towards the undisputed heavyweight champions of the universe. Remember how the massive blue stars lived fast and died young? We are now seeking out the stars that took that to the absolute extreme, the hypergiants and supergiants that dwarf everything else. You need to adjust your perception of scale entirely. The red giant we just observed was massive, expanding perhaps to the orbit of Earth. But these hypergiants are on a completely different level. They are truly, mind-bogglingly huge. Our first colossal destination is UY Scuti. Imagine the star we just left, the red giant, now shrinking back to the size of a marble. UY Scuti would be a vast, kilometer-wide sphere by comparison. UY Scuti is currently the largest known star by volume, a truly immense red supergiant located in the constellation Scutum, thousands of light-years away in the plane of the Milky Way. If you were to place UY Scuti at the center of our solar system, its surface would extend far beyond the orbit of Jupiter, perhaps even challenging the orbit of Saturn. This scale is so impossible, it almost feels like a joke the universe is playing. One light joke: it's so big, if you tried to drive around its equator at highway speed, your great-great-great-grandchildren would still be making the trip. A solid historical fact is that UY Scuti is also a variable star, meaning its brightness changes over time. Its status as the largest known star is based on estimates of its size, derived from its brightness, distance, and temperature, with its radius currently estimated to be around 1,708 times the radius of the Sunday. That's a curious detail. 1,708 times. That means it has a diameter of roughly 2.4 billion kilometers. Despite its immense size, UY Scuti is not the most massive star. It's a very bloated star that has already consumed most of its core hydrogen and is nearing the end of its life, having swelled up to this incredible size. Its sheer size means its outer atmosphere is extremely diffuse and weakly bound by gravity, and it is losing mass at a tremendous rate through powerful stellar winds. You are now bathed in its dim reddish light. Because it is so vast, its surface gravity is actually quite low. If you could float near the surface, the force of gravity would be surprisingly weak, far less than what you'd feel on a star like the Sunday. This lack of gravitational pull is why those outer layers have expanded so far and are constantly blowing away. Historians still debate whether stars like UY Scuti retain a stable layered structure or whether deep-seated convection currents cause the star to slosh internally, leading to its observed variability and making its exact size difficult to pin down precisely. The intense low-frequency light emanating from this star is a stark reminder of the extreme physics at play. You remember that faint starlight at the beginning, when you were in the GMC? The light from UY Scuti is perhaps 1,000,000 times brighter, yet because of its enormous distance and the dust between us, it's not visible to the naked eye. This star is not long for the universe. Its core is now fusing heavier elements, accelerating toward an eventual, catastrophic supernova explosion that will enrich the galaxy with elements vital for future stars and life. Leaving the enormous, red, billowing atmosphere of UY Scuti, we travel over 160000 light-years away, out of the main disk of the Milky Way galaxy, and toward one of our closest neighbors, the Large Magellanic Cloud, LMC. This small satellite galaxy orbiting the Milky Way is a vibrant region of star formation and where we find our next cosmic titan, WOG 64. This star is another monstrous red supergiant, often included in the list of the largest known stars, and it presents a slightly different, equally impressive set of characteristics compared to UY Scuti. WOAG-64 is known for being extremely cool, intensely luminous, and, crucially, being almost completely surrounded by a gigantic, thick torus of circumstellar dust and water ice. This cloud of dust is so opaque that WOHG-64 is almost invisible in optical light. You are now floating in this vast, swirling envelope of material. It's a bit like wandering through a cosmic sauna, where the steam is incredibly cold dust. This massive shell of dust, shed by the star itself through its powerful stellar wind, is estimated to be over a light-year in diameter. It's a remarkable illustration of how much material these giants eject into the surrounding space as they age. This constant, heavy mass loss is one of the definitive traits of a late-stage red supergiant. A solid historical fact is that WOHG-64 was initially discovered in the 1970 seconds by astronomers searching for extremely red objects in the LMC, but its true colossal size and the nature of its dust envelope were only fully understood and characterized through infrared observations made by telescopes like the Very Large Telescope in the early 2000s. The infrared light, the heat, is the only radiation that can penetrate that thick, dusty shell. Its sheer luminosity is what sets it apart. While its radius is massive, estimates place it around 1,540 times the radius of the Sun. Its brightness is staggering, potentially exceeding 4,90000 times that of the Sunday. This puts it among the most luminous stars known, pumping out an incredible amount of energy despite its low surface temperature, which averages around 3,000 Kelvin. A curious detail is that the dust surrounding WOHG-64 contains water and complex molecules. This material, which was once inside the star, will eventually be dispersed into the Large Magellanic Cloud, potentially forming the next generation of stars, planets, and perhaps even seeding that region with the ingredients for life. The star is sacrificing its own body to enrich its galaxy. Historians still debate whether the complex chemical structure of the dust shell around WOHG-64 indicates a recent rapid and massive ejection event, perhaps triggered by core instability, or if it represents a long, steady wind of mass loss. You might find yourself thinking how ironic it is that the largest, brightest objects can hide themselves so effectively behind their own shed skin. One light joke: it's the ultimate cosmic introvert, so bright it has to wear a light-blocking dusty cloak just to go outside. The gravitational struggle here is constant. The outward pressure of the light is barely contained by the star's immense gravity, leading to this continuous, powerful mass loss. Leaving the dusty embrace of WOHG-64 in the Large Magellanic Cloud, you now journey back toward the heart of the Milky Way. But you stop short in the constellation of Monoceros, the unicorn, to witness a star that, while not the largest by volume, offered humanity one of the most visually stunning and dramatic spectacles in recent memory. V838 Monocerotis, V838 Mon. This is a star known not for its steady state, but for a singular, massive, and highly mysterious outburst that occurred in 2002. You are now floating in the wake of that event. In January of that year, V838 Mon suddenly and dramatically brightened, eventually becoming nearly 6,000,000 times more luminous than the Sunday. Unlike a supernova, where the star explodes and dies, or a nova, which is a recurring event on a white dwarf, this was something altogether different. The star simply inflated rapidly to enormous size, briefly becoming one of the largest stars in the galaxy, before quickly fading back down. The truly extraordinary aftermath of this explosion is what you are now seeing, a light echo. The light from the 2002 outburst rushed outward into space and illuminated the layers of dust and gas that the star had previously ejected into its surroundings. Think of it like a three-dimensional cosmic flashbulb that briefly lights up everything around it. Because the dust clouds are at various distances from the star, the light reaches them and is reflected back to us at different times. You can see this wave of light propagating outward through the interstellar medium, continuously revealing new, intricate, and beautiful structures in the surrounding dust cloud. This phenomenon provided scientists with an unparalleled opportunity to study the star's environment. A curious detail is that the appearance of the light echo is an illusion of motion. The dust itself isn't moving at the speed of light, only the illumination is traveling outward. It's the light itself bouncing off stationary structures, allowing us to see the geometry of the pre-existing dust shell. This is a solid historical fact that was captured and visually confirmed by the Hubble Space Telescope, which took some of the most iconic images of the 21st century, visually mapping the echo's expansion over the course of several years. The star itself, now that it has calmed down, is a cool, extremely luminous, and swollen M-type giant, although its mass is still debated. Historians still debate whether the outburst of V838 Monocerotis was caused by a late thermal pulse from a dying star, a merger event between the star and a companion star or giant planet, or a highly unusual surface helium flash. The prevailing theory leans toward a stellar merger, where the star essentially ate another star. You might joke that the star simply had indigestion after swallowing too much companion, leading to that massive celestial burp. The star is still radiating that beautiful reddish-orange light onto the vast glowing dust clouds, creating a silent, shimmering monument to a very unique stellar event. Drifting away from the fading light echo of V838 Monocerotis, you set a course for the constellation of Cepheus, a northern constellation that holds yet another enormous stellar specimen, RW Cephei. This star is classified as an orange hypergiant and is one of the most luminous and physically largest stars known to humanity. It offers a slightly different color profile than the previous red giants, sitting closer to a warm, deep orange on the stellar temperature scale. You approach RW Cephei, and the sheer scale once again demands a mental reset. While its exact size is constantly being refined by new data, estimates place its radius around 1,535 times that of the Sunday. This means, like UY Scuti, if placed at the center of our solar system, its atmosphere would engulf Jupiter. The massive size, coupled with its classification as a hypergiant stars that lie right on the edge of stability, tells a story of continuous heavy mass loss and an intense, precarious existence. The color is beautiful, a deep, rich orange, indicating a surface temperature that is hot but cooler than a yellow star like the Sun, probably hovering around 4,000 Kelvin. A solid historical fact is that RW Cephei is a member of the same class of massive, luminous stars as VV Cephei and Mu Cephei, the Garnet Star, which are characterized by their enormous size and the spectral characteristics of their dense atmospheres. Its high luminosity is estimated to be over 3,000,000 times that of the Sunday. This phenomenal output means that the star is producing immense amounts of energy, putting extreme pressure on its own structure. A curious detail about orange hypergiants like RW Cephei is the instability they experience. They exist in a region on the Hertzsprung-Russell diagram called the yellow evolutionary void, a zone where stars are predicted to be highly unstable as they transition between blue supergiant and red supergiant phases. They pulsate, they vary in brightness, and they are constantly shedding material. This shedding forms a complex, extended atmosphere and circumstellar dust shell that makes precisely measuring the star's edge, and therefore its exact radius, a challenging endeavor. It's like trying to measure a cloud. Where exactly does the star end and space begin? One light joke. It's the star that has a perpetual bad case of stellar allergies, constantly sneezing out its outer layers. Historians still debate whether the pulsation and variability seen in stars like RW Cephei are primarily due to internal changes in core fusion rates, which drive expansion and contraction, or if they are caused by magnetic activity and surface phenomena. The high rate of mass loss from RW Cephei is a certainty, however. It's not just growing old, it's literally blowing itself apart at a rate that is rapidly enriching its section of the galaxy. This is a star living life on the absolute edge, a ticking celestial time bomb, slowly but surely preparing for its final, inevitable collapse and glorious supernova. The intense light and the vast scale of this orange titan are a testament to the extremes of stellar engineering in the universe. You have traveled across galaxies, witnessed the birth of stars, the quiet death of solar mass dwarfs, and the precarious, bloated lives of some of the largest supergiants and hypergiants known. Now, for our final destination, you must journey to the heart of the Milky Way itself, into the tumultuous, high-energy environment of the galactic center. Here, amidst dense clusters of young, massive stars, we encounter the Pistol Star. This is the star that closes our list. Not necessarily because it's the largest by volume. Its radius is estimated to be around 300 times that of the Sun, but because it is one of the most luminous and massive stars ever discovered, truly reigning as a powerful celestial giant. The Pistol Star is a magnificent blue hypergiant, shining with the power of nearly 3 million suns. Its phenomenal brightness makes it one of the most powerful stars known, second only to a few other colossal, short-lived hypergiants. You are now bathed in its blinding, fierce, blue-white light, which is so intense it's actively blowing huge amounts of material off the star itself. This expelled material forms the spectacular surrounding structure known as the Pistol Nebula, which the star's radiation has energized and pushed outward. The nebula is visible as a glowing bubble of gas and dust surrounding the star, a testament to its furious energy output. A solid historical fact is that the Pistol Star and its nebula were not confirmed until the 1992, and only through infrared telescopes. Why? Because the star is located only about 25,000 light-years away, but the intense amount of dust and gas lying between us and the galactic center completely absorbs its visible light. If there were no intervening dust, the Pistol Star would be easily visible to the naked eye, shining as bright as the planet Mars, despite its colossal distance. The Pistol Star is truly massive, estimated to be anywhere from 80 to 100 times the mass of the Sunday. This huge mass dictates its violent, short life. It has already ejected about 10 solar masses of material in massive bursts, creating the nebula around it. It's burning through its nuclear fuel at a reckless speed, and its total lifespan is likely only a few million years. You might wonder, why are so many of these extremely massive stars so unstable? The immense energy output puts them right up against the theoretical limit where a star's outward pressure from light is so great that it nearly overcomes gravity entirely, leading to these constant, massive eruptions of gas. One light joke: the Pistol Star is the rock star of the galaxy. It's so bright, it has its own permanent entourage of glowing gas and dust. A curious detail is that the existence of the Pistol Star and other massive stars near the supermassive black hole at the galactic center, Sagittarius A*, challenges some conventional theories about star formation. Historians still debate whether these massive stars formed in situ right where they are now, or whether they were driven toward the core from further out, perhaps through gravitational interactions with other stars. The environment is so extreme, with intense radiation and gravity, that star formation should be difficult, yet here they shine, intensely and briefly. The 5 largest stars, known to humanity by volume, and with the caveat that these sizes constantly shift with new observations, are often cited as including UY Scuti, the largest, WOHG 64, V838 Monocerotis at its peak, RW Cephei, and sometimes Mu Cephei or KY Cygni. But the common thread linking all these titans, including the immensely luminous Pistol Star, is their extreme mass, their powerful stellar winds, and their inevitable spectacular fate. A cataclysmic supernova explosion that marks the end of their lives and the dispersal of the heavy elements they have forged. The blue light of the Pistol Star begins to soften, shifting in your perception to a deep, calming sapphire, and the massive, billowing nebula seems to slow its outward crawl. Feel the great silence of the cosmos return, a silence that absorbs the sound of these titanic events, leaving only a sense of profound scale and calm. The immense gravity of these giants fades from your awareness, replaced by the gentle, even pull of your own bed, your own comfortable planet. We have wandered the long, slow roads of stellar evolution, from the cold, dark beginning in a giant molecular cloud to the fierce, blinding short lives of the galaxy's biggest stars. All of these behemoths, whether red or blue, hypergiant or supergiant, were simply following the destiny dictated by their initial mass, all moving inexorably toward a final, brilliant act of dispersal. You are now simply floating, no longer a consciousness bound by cosmic physics, but simply you, here, now. The images of swirling gas, fiery cores, and immense bloated atmospheres are growing distant, becoming no more than quiet, warm echoes in the dark. Let the scale of the universe comfort you, knowing that your small, stable corner of it is perfectly balanced and utterly safe. The stars will continue their dance, but for now, you can rest. Drift now, let the thoughts slow, and let the gentle rhythm of your breathing guide you back to sleep.